Morning, everybody. So in this session, we are very glad to have Professor Bob Holdom from University of Toronto. He will talk about ghosts on the way to a gravity QFT. Let's welcome.
Thank you very much. The main question for this talk is, can quantum gravity be a quantum field theory? And last week, I think we heard a few answers to that question, and it was quite a resounding no. Perhaps they meant that a quantum field theory based on the Einstein theory is non-renormalizable and thus not UV complete, which is certainly true. And that theory is only okay as a low-energy effective quantum field theory. But there is a better candidate, and all you have to do is add terms quadratic in the curvature to the Einstein action. There are two such terms, which brings in two coupling constants. And when I say add terms quadratic, I mean only terms quadratic. Don't add any higher power terms in the curvature. So such a theory could be called quantum quadratic gravity, and it was seen to be a renormalizable quantum field theory a long time ago. Now, very recently, there's been a new calculation of the beta functions in this theory, and both of the two couplings are found to be asymptotically free. Of course, there's a whole flow diagram of how the couplings can run, but on that diagram, there is a line where both couplings are asymptotically free. If that's true, then this theory is UV complete in the simplest possible way. It's an asymptotically free quantum field theory, just like QCD. But there is a stumbling block. This theory has a ghost, a massive spin-2 partner of the graviton. And by ghost, I just mean what looks otherwise be a normal field, but it just has the wrong sign kinetic term. Now, if you try canonical quantization, that leads to a so-called negative norm state. And that's thought to be a problem. But I think from what I've just said, there's a lot of motivation to really understand this problem more. So that's what I'll be doing in this talk. First of all, some problems not caused by a negative norm state. Instability. That is not caused by a negative norm state. The classical theory is unstable, but the point of the quantization is to trade that instability of the classical theory for a negative norm state of the quantum theory. And when you do that, then all perturbative states have positive energies. So I'll be going through that. The other thing you may often hear is so-called loss of unitarity. Well, that's not true either. A ghost theory has S matrix unitarity. When you write that condition down, the unit operator there is the one that comes out of the completeness relation. The completeness relation does reflect the negative norm. Okay, so what is the problem? Well, it's the Born rule. So I've given the Born rule there, and negative norms can produce negative probability. For example, if the initial norm is positive and the final norm is negative, or vice versa, then you get a negative probability. So let's call the sign of the norm of a state the ghost parity of that state. So we can first consider theories that preserve ghost parity. So for a theory that preserves ghost parity, the norm of the initial state and the norm of the final state have the same signs. The ghost parity does not change. So in those theories, the probability is always positive. So that shows that there is a probability interpretation even with negative norm states. Now, we're more interested in the other kind of theories that violate ghost parity. That quantum quadratic gravity would be such a theory. And for these theories, something more is needed. So that's what I'll be talking about. And to try to address this issue, let's go back to quantum mechanics, which can be viewed as a 0+1 dimensional quantum field theory. And this problem with PQG that I've been talking about has already brought focus on some extensions of quantum mechanics. There's PT-symmetric quantum mechanics, discussed by Mannheim and Bender, and a so-called Dirac-Pauli quantization, also discussed in the same context by Salvio and Trimio. So we're going to just follow a canonical quantization that's geared to a ghost theory, and then just see where it leads. So we'll find that our path will sometimes overlap with one or the other of these two other approaches. So let me give you the basic picture. So we all know that unitary evolution is fundamental to quantum mechanics. The spectrum of the theory and the correlation of functions that are of interest in quantum field theory are all consequences of the unitary evolution of the theory. But the formulation of the Born rule to obtain probabilities is something separate. It's a separate aspect of quantum mechanics. So if that's the case, then the Born rule may be modified independently of the unitary evolution. So it could be modified while keeping everything that we already know about the theory that follows from unitary evolution. So the real question, is there a sensible modification, a modification that leads to a sensible Born rule? And is such a modification unique? So for the outline of the rest of the talk, I'll set up the theory, identify two apparent problems, and then show how the following two things can arise: a positive spectrum at weak and strong coupling, and a positive inner product. And then three other topics I would like to get to. I'll show how to obtain wave functions in a coordinate representation. I then can compare spectra with the PT-symmetric quantum mechanics. And finally, I will consider the case of complex conjugate energy eigenvalues. So setting up the theory, I just introduced this parameter sigma can be plus or minus 1. So it's 1 for a normal theory and minus 1 for a ghost theory. And this parameter in the Hamiltonian just shows up in one spot. It multiplies the quadratic terms in the Hamiltonian. So everything else on this slide is completely standard. These commutation relations and the relation between the original fields and the annihilation and creation operators. So the difference comes in when you think about what the Hilbert space is and construct the occupation number basis. So for normal theory, we know how that works. And you see in the ghost theory, all we do is interchange A dagger and A. So the vacuum state is defined by the A dagger acting on it to be 0. And the other states are built up with powers of A. So that's just a definition, and given what I defined on the previous slide, then we can work out everything. And for example, the norms of the states, when sigma is negative, we'll have alternating signs. So the sigma enters in two other ways. The completeness relation, as I mentioned before, involves the norms, and so powers of sigma will show up there. Also, if we expand the general state in terms of the occupation number basis, and then solve for these expansion coefficients, then powers of sigma will also appear there. Now, I should mention that there are different looking, but I think equivalent ways to quantize ghosts, and you'll find another example in this paper where you'll find the notation is quite different. So I'm going to try to set up a matrix notation. So let's introduce an infinite matrix bold A and an infinite column vector bold psi. So the components of these objects in the first case are just the matrix elements of the operator and these expansion coefficients. I also will introduce a matrix bold eta, which just has powers of sigma on the diagonal. So in particular, eta minus is the ghost parity operator in the occupation number basis. Another thing, if you take an operator product, then in matrix notation, after introducing a complete set of states, that brings in this matrix eta. Also, we can just figure out explicitly what these various matrix version of operators look like. For example, phi-fold is this matrix that depends on sigma in this way. So I think I've given you a good sense of how everything depends on sigma. And from now on, I'll just drop the sigma subscript. And for the most part, I'll be talking about a ghost theory. So first of all, the inner product in matrix notation again brings in the eta matrix. We can write it in one of these two ways. Often I'll use this way. With the inner product, we can define what self-adjoint means in the usual definition here. But in terms of matrices, it looks like this. When I say something is Hermitian, I'll just mean Hermitian in the usual sense. So for a matrix, it's A dagger equals A. Now, if A is a self-adjoint operator, or matrix in this case, then there's another matrix which I can define as A twiddle is just eta times A. That turns out to be Hermitian. And if A is Hermitian, then there's another matrix, again A twiddle, which turns out to be self-adjoint. Now, it turns out that the gross Hamiltonian is Hermitian in the usual sense. It's not self-adjoint. But there is another matrix, H twiddle, which will be self-adjoint, and we'll see that that plays a central role. So, for example, in unitary evolution, the evolution of an arbitrary state. So if you translate that into the evolution of this column vector, then we find the H twiddle matrix that appears. And if I consider this row vector, it also transforms according to H twiddle. But these two factors are factors in the definition of the inner product. So you can see that the time-dependent inner product, the time dependence canceled out. And that's consistent with unitarity. It's certainly a property of normal quantum mechanics. Same kind of thing works if we look at energy eigenstates. Let's say the energies En and the states n bar are the eigenvalues and eigenstates of the full Hamiltonian. And then translate that into matrix notation. So let these n bar states be these column vectors with a superscript n. And again, it's the H twiddle that appears. And there's another type of matrix or eigenvalue equation we can write down for these row vectors. And here it's the complex conjugate energies that appear. So we're then talking about two different types of energy eigenvectors just because this matrix H twiddle is not Hermitian. So these are the right and left eigenvectors, respectively. Putting these two together, it's not hard to see that En must be real, except when the norm vanishes. And there's nothing stopping the norm from vanishing, so it seems we do have an issue here to face, what to do with complex energies. So I'll come back to that, but let's move on to the Born rule. Born rule gives a probability for a transition from some state I to some final state F. And using our inner product, this is what it would look like. Now, if you sum over the final states, it gets unity automatically. That's basically a statement of the unitarity of the theory. And it's also related to a completeness relation. But it does not ensure that any particular probability is between 0 and 1. So we failed to get a probability interpretation so far. So we have then these two apparent problems. Energy spectrum is not guaranteed to be real, basically because this matrix is not Hermitian. And we have negative norms. And if you look at the energy eigenstates, we'll be finding that their norms also alternate in sign, just like they do in the occupation number basis. Okay, so first of all, let's look for when and where and if these complex energies occur. And then I'll come back to negative norms. So let's get back to this H-twiddle matrix. It's obtained from the operator H by replacing the operators phi and pi by these matrices. Now, if you just focus in on the quadratic part of H-twiddle, it involves these non-Hermitian matrices. And this combination effectively brings in another factor of sigma. And so what comes out is just m times this matrix, which is just the normal positive energy free spectrum, which is therefore true for either value of sigma. And this coming out is the reason why we chose that particular quantization that we did. So let's move on to interacting theories. First of all, interactions with an even power of the phi twiddle. So we have the quadratic part I just gave and this interacting term. Now it turns out that this theory does happen to be such that it's Hermitian. This matrix is Hermitian, and therefore it's going to generate real spectra automatically. It also turns out to be the case that it conserves ghost parity, or in other words, H-twiddle commutes with this eta matrix. So this is an example of a theory where all probabilities are automatically positive, even with the presence of negative norms, showing that these things can coexist with a sensible probability interpretation. If you look a little more closely at these theories, though, the normal and the ghost K-even theories, they do have different H-twiddles, but using the methods I'll get to in a little while, we find that they are isospectral, so they have exactly the same spectra. The full propagators of the two theories just differ by a sign. Amplitude, the 2, 6, or 10 ghosts just differ by a sign from the corresponding amplitude in the normal theory. So with only these minor changes of various signs, it seems to me that the ghost theory with ghost parity seems physically equivalent to the corresponding normal theory. So it just seems like these ghost theories are just a funny way to write a normal theory. So let's look at the K-odd theories. In this case, the normal and the ghost theories are distinctly different. Now, if you look at the normal K-odd theory, for example, by cube theory, that has a well-known problem. The spectrum is not bounded from below, at least for lambda sufficiently large. And now, if you look at the ghost theory, we finally have a theory where the Hamiltonian H-twiddle is not Hermitian. So in addition to this not bounded from below problem, it would seem that we also have another problem with complex energy theory. But these looks are deceiving. In fact, the K-odd ghost theory enjoys a positive real spectrum for any coupling. So to see how that works, we have to look at a little numerical study of the K-odd ghost theory. So numerically, to approach this, we truncate the Hilbert space by truncating the matrix to a finite size, and then we can diagonalize it and just look at what the eigenvalues are doing as you just keep increasing the size of this finite matrix. And what we find is that the lowest set of eigenvalues, there is some lowest set of eigenvalues which are all positive and real, and that set of eigenvalues just keeps growing as the size of H-twiddle keeps growing and growing. So for example, a matrix size of 600 by 600, the first 40 eigenvalues are all real and positive for both real and strong coupling. And as you make this matrix larger and larger, the ones that are not real and positive, the complex ones, are just being pushed up more and more up to infinite energies in the infinite size limit. So that's why I'm claiming that we can say that the spectrum of the actual theory, which is the infinite size limit, is real and positive.
Theory. How do you define this as spectrum, given that it's not bounded from below?
This spectrum, I'll show some more examples in the next slide. This is bounded from below. So the ghost theory cured that problem of the normal theory.
I see. So you're saying, so the normal theory doesn't have well-defined a spectrum, but the ghost theory does.
Yeah.
Thanks.
So here's some numerical results, not for the first 40, but the first 10 eigenstates. And for weak coupling, 110, and strong coupling of 10. So I'm giving the energy eigenvalues, so you can compare the weak coupling values to the strong coupling values. And you see that the interactions, as they get stronger, just push apart the energy levels. So it's the case where these energy levels actually could merge as the coupling changed. That's the case where you would have problems. You would possibly generate complex energy eigenvalues. But you see that's not happening here. They just get pushed further apart. Now, what are these Zn factors? Well, these Zn factors are defining what the full propagator is. So here's an expression for the full propagator. There's a vacuum term and a sum over the Zn factors times the Feynman propagator. This is a free Feynman propagator in 0 + 1 dimension. And in place of the mass, we're just putting the energy of that corresponding state. So once we have if we're still in the finite case where we can numerically find everything, the eigenvalues and the eigenstate, we plug into this formula for Zn, so we know what the Zn's are, and that's what gave us these values. So you see these Zn factors alternate in sign, and the largest one, the first excited state, dominates and is the only contribution in the free theory. Even in the strong theory, it still dominates. The other thing you notice is these values quickly get small as you go up to higher states. So you don't need very many of them to get an accurate full propagator. Okay, so I think that summarizes what happened to the first question we had. Are there complex energies? And we're finding, at least in the infinite size limit, that there are not complex energies in these particular models. Now let's move on to the problem of negative norms. So we approach that by just coming up with a new inner product. Once you have a new inner product, that defines a new Born rule. So let's call the new inner product the G inner product, standing for ghost. So in the matrix form, that involves a Hermitian matrix bold G, again written in two different ways. We can write it in a third way, introducing another matrix, G twiddle, again eta times G. In this case, G twiddle is the additional factor that we insert into the old inner product to get the new inner product. So then when we ask, how do we arrange this new inner product to be preserved in time? It's easy in this way of writing it because we just need the H twiddle to be able to commute through this new factor. And so if that's true, then this new inner product is preserved in time. So G twiddle has to commute with H twiddle. And that means that the energy eigenstates are also eigenstates of G twiddle. So we're trying to figure out what this G twiddle is. So now we can use this fact that G twiddle, or this fact that we know what the eigenstates are. So we are then free to choose the eigenvalues to do what we want, which is to change the sign of the norm. And that will occur if the eigenvalues are just -1 to the n. So that helps you to determine what G twiddle is. If you wanted an explicit realization, well, here it is. So this is the realization in the occupation number basis. It's the sum of terms, or in the numerator, this is a matrix because I have a column vector times a row vector. And in general, this is a non-trivial matrix. All entries are typically non-zero. And if you square this matrix, you'll end up with this without the absolute values, and that's just the completeness relation, given 1. Some other things, these relations say that this G twiddle is self-adjoint with respect to the G, this new G inner product. And then H twiddle also ends up being self-adjoint with respect to the new inner product. They're also self-adjoint with respect to the old eta inner product. Now, for us, I guess the thing we're mostly interested in is the fact that this matrix G is a positive definite Hermitian matrix, which you could easily see from the previous explicit result. So that's what's going to give us a sensible Born rule. We can make things even simpler by noting that now in the energy eigenstate basis, this inner product, since we've reversed the sign of the norms, this is just delta mn. So if we write a general state in terms of these energy eigenstates, so this defines new expansion coefficients with a twiddle, define new column vectors, then the inner product just becomes the Dirac inner product if we happen to use this basis. So that certainly does give us a sensible inner product. It is not the same Born rule as before, though, because we have to go through a different procedure to find it. Whoops. We have to find out the full energy eigenstate of the full Hamiltonian and use that as a basis. And then we end up with the standard looking Born rule, which obviously is positive definite and works as a probability interpretation. If we don't want to do that, we can just work directly in the occupation number basis, which means we use this matrix G, which gives the same result. Okay, so I think we managed to deal with this other problem. And by the construction that I just went through, it seems to me that this is unique. So this is a unique definition of the inner product and the Born rule in this theory. Let's move on to finding wave functions. So first of all, how do we find observables in this theory? So a standard eigenvalue equation for some operator translated into matrix notation again brings in the A twiddle. So for the eigenvalues to be real, we want A twiddle to be Hermitian in the usual sense. So if A twiddle is Hermitian, then the original operator has to be self-adjoint. So that's the rule this is giving us. Only self-adjoint operators can be observable. On the other hand, that was not true for the Hamiltonian. It was Hermitian. And the fact that this Hamiltonian still gave us real eigenvalues, at least in the infinite size limit, that seems to be an exception to the rule. So, but for now on, we're going to be looking at self-adjoint operators as observable. So for the coordinate representation, we can just consider the commutation relation between some Q and some P. At this stage, we don't know what those operators are. In matrix notation, it looks like that, or in twiddle notation, it looks like that. And we then just look for solutions of that equation. There turn out to be two sets of solutions for these Q twiddles and P twiddles. Either they're the original field phi and pi, or I phi twiddle and I pi twiddle. And as I said, these Q twiddle things should be Hermitian, and in fact they are. These are all Hermitian matrices. So that means the original operators are self-adjoint. So we have two sets. Now, it turns out the second set is what it corresponds to the so-called Dirac-Pauli choice. So let's go with that for a while and consider constructing both the eigenvectors and the eigenvalues from this equation using this matrix. So the eigenvalues are the set of real positions, guaranteed to be real now, and the eigenvectors I'll label with the column vector with the superscript x. So with these eigenvectors, we can now construct wave functions for any state we want, but let's look at the exact energy eigenstates. So the wave function then is just the inner product between these coordinate eigenvectors and the energy eigenvectors. That will be a function of x. And the position wave functions, sorry, the momentum wave functions can be obtained in a similar way. So, but first of all, note that I'm talking about the exact energy eigenstates. So they do depend on the coupling. So these wave functions are going to depend on the coupling. So let's first of all look at zero coupling. So I'm giving the wave functions for the ground state and the second excited state. So that looks like this. And because I'm at zero coupling, the momentum wave functions are the same. Now, if you go to non-zero coupling, lambda equal 1, yes, I think, well, no, these are, well, not this, yeah, this is zero coupling, so that's harmonic oscillator. But this is an interacting theory, so these are new. Yeah, we're still looking at the k odd theory, and in this case, it's k equal 3. So it's a cubic
It's a phi cube.
phi cube theory, yeah. A ghost phi cube.
But this is symmetric, so somehow the symmetry is not broken by the phi cube.
Well, just a second.
Okay.
It's interesting you bring that up. It wasn't obvious to me that phi cube could break parity. Did you think it's automatically going to break parity? Okay, well, yeah, so let's just compare these to the others, and what's happened, the wave functions have become more localized. So now if you look at the momentum ones, you expect to be more spread out. But you've already guessed that something else is happening and parity is being broken. Now, so why is parity being broken? It's obvious to you, but it turns out that the eta acting on these momentum wave functions, or sorry, momentum eigenvectors, do just reverse the sign of heat. And we've already said for these theories that eta does not compete with H, with them. So this shows that whatever we're calling normal parity is being broken in the theory. Okay, so that's the next comment is, if you go to the other choice, remember I said there are two solutions. In the other choice, it's broken in the coordinate wave function instead. You can ask what the G inner product is doing. It doesn't do anything as long as you're looking at the absolute value of these wave functions. A few other comments. The eta inner product in the coordinate basis, so x prime and x, is delta minus x prime. So that's not a diagonal matrix. It turns out to have negative eigenvalues. That's not surprising. In the other, in the occupation number basis and the full energy basis, we also got negative eigenvalues, which are negative norms.
Yeah, I have a question that may be related to Nyanir's question. So the x you're plotting is I times the original field, right?
X is just a eigenvalue.
But it's the eigenvalue of I phi, not of phi, right?
It's I phi twiddle, yes.
Yeah. So let me just ask, as a mathematical exercise, suppose I just decided to study the theory with a normal positive kinetic term, but with a cubic interaction that is I phi cube. Will I get the same wave function that you're showing?
Yeah, in that case, the Hermitian operator would, I guess, just be phi.
Yeah, okay.
And yes, you would get the same.
Okay, thanks.
If we consider this x prime x inner product with the G inner product, again, now that's something that depends on the coupling, but whatever it is, it does not have negative eigenvalues, as expected, because G is positive definite. And it's only when the coupling vanished that you finally go over to the standard looking result, which is just the delta xx prime. Okay, so that's first of the three topics I wanted to get through. Then here's the second one, the connection with PT-symmetric quantum mechanics. Now, in those studies, the determination of a sensible inner product using the eigenstates of a non-Hermitian Hamiltonian arises in those studies. So that sounds very similar to what we're doing with the ghost theory. On the other hand, those studies use some kind of complex extension of ordinary quantum mechanics by the construction of a complex coordinate space representation. So they actually don't end up talking about these real values for position that I'm talking about. And so what's the similarity? Well, the ghost theories, they instead start with a Hermitian Hamiltonian and a canonical quantization, and it's the effect of the negative norms that brings in this non-Hermitian H brittle. So that's the similarity, that we end up dealing with an H brittle, which is somewhat similar to what they start off with. It's a non-Hermitian Hamiltonian. Like, so yeah, this is an example. This is what the theory that you were just bringing up. It would have positive kinetic terms, and if we just go through with what we're used to doing now, we just choose the sigma equal 1 canonical quantization. So we can do that, but right away you run into a blockage. The norms that come out are just not preserved in time, which is kind of obvious because you don't have a Hermitian Hamiltonian. And a major theme of these studies then is to find an inner product that is both positive definite, which is what I was doing, but at the same time also time independent. So in contrast to the ghost theory, the unitary evolution of the PT theory is not built in as it was in the ghost theory. Let's compare these theories via the spectra. So I said I can quantize the PT theory, and so then I can do all the same things I did with the ghost theory. And I end up finding the spectrum matches. A few little differences. The full propagator is a negative, the ghost propagator. And so all this is not surprising because you get the chaotic ghost theory is transformed into the PT theory just by multiplying the fields by I. So to me, it seems like the two quantum field theories are equivalent. That is, if you define the inner product in the PT theory in the way that does correspond to what's going on in the ghost theory. There are other examples. So the PT literature has various spectra given in the literature. For example, this is kind of a massless version of our, well, it's a massless version of a PT theory, which corresponds to a massless version of our ghost theory, chaotic ghost theory, when epsilon equal 1. So all the spectrum matches. What is in the literature matches what I find when I quantize in the way I'm talking about, and the same here. There are other theories in the literature. Here's something that looks like a higher derivative theory, and there's a corresponding higher derivative ghost theory. And again, all the spectra match when epsilon equals 1. So that's probably the main point here is epsilon equal 1. So if only those particular PT theories that I'm talking about that are connected to being ghost theories, and these particular theories in terminology of that literature, they have Stokes wedges that continue to include the real axis. So you don't have to know what that means, but it's just a feature of these theories that happen to have corresponding ghost theories. And I mentioned that eta and the G inner products do carry over to the PT theory, but in a sense, you're actually defining how to calculate any matrix element. So it's just not quite that trivial. And like you were bringing up, the construction of the coordinate representation also carries over to the PT theory. So in other words, you don't have to go through the complex construction that they usually go through. Okay, now that's how much time do I have? Oh, good. Okay, lots of time, so I'll finish early. So the third topic are to consider spectra with complex conjugate pairs. Now, why in the world would I want to do this? I did mention in passing that in the chaotic ghost theory, when H twiddle was truncated, there were such pairs of eigenvalues. And so why are those interesting? Well, in 4D quantum field theory, something similar happens. And there are propagator poles at complex conjugate locations that appear when there's a one-loop correction. And that's well understood in normal quantum field theory, but the meaning of this when it happens for a ghost theory is still a subject of debate. So various authors still do not agree what this means. So I'm just saying it, we have a simple little model now that we have these things in them, and we should just look at those things. So way back I said that these energies can be complex only when the norms vanish. So let's label a pair of these states by p and p plus 1, so the norms vanish. But these off-diagonal norms do not vanish, or off-diagonal inner products. Okay, so we now have two kinds of states, these new p states and the original q states. These original q states still have alternating sign norms as before. So it's convenient to define new states that do have diagonal norms. So these new states that are not energy eigenstates anymore, they're combinations of energy eigenstates. So they're combinations with these phases. And first of all, let's define beta, the beta phase to be such that these two states are orthogonal. And then we find that their norms are these results. So one is the negative of the other. So only one and only one of these norms is negative. Now we still have this other phase to play with. So let's choose that so that the corresponding state, that linear combination, has no overlap with phi acting on the true vacuum. Or in other words, let this matrix element vanish. So in that case, the state does not contribute to the spectral representation of the full propagator. And in a higher dimensional quantum field theory, and another implication of this is that that state is not an asymptotic state. And asymptotic states are those states that can participate in a scattering experiment. Okay, so what about a positive inner product with these strange complex eigenvalues floating around? Well, again, we would require this condition, but H twiddle is no longer diagonal in the spaces that we're talking about. So that means we have less freedom in the choice of D twiddle. And in fact, G twiddle can only change both of these signs, these eigenvalues. These eigenvalues have to be the same for both states, either both plus and both negative. Okay, so that's still 1 degree of freedom, and that's enough to choose the G norm so that the beta state is positive. And then it's only the alpha states, the states that are not asymptotic states, that have negative G norm. And here's the explicit representation for this G twiddle matrix. So going back to the Born rule, well, if we restrict ourselves to the space of asymptotic states, I think you can see why things are going to work in that case. We just do all the same things we did before. And then we'll end up with this standard Born rule. So we've been able to avoid that negative norm state because it's not an asymptotic state, the alpha state. The full propagator now has contributions from these p states, and these ZP factors are small when these states are higher up in the spectrum. These ZP factors get smaller and smaller, but they're there. If there's a sum rule, so they add up in this way, and this combination that appears in the sum rule, again, only involves the beta state, not the alpha state. And the sign of this real part of Z, P, is determined by the original norm of that beta state. So just like over here, there were negative contributions to the propagator, as we saw numerically too. And there are also effectively negative contributions, possibly, when these things are negative. But this new propagator then has contributions that contain factors like this, either sign of the imaginary part of this energy. So these are they can be exponentially growing factors in the propagator. On the other hand, the inner product has been constructed to be time independent, and that's still true. And this strange result in the propagator is still consistent with unitarity and a sensible Born rule. Okay, so that's about it. So I guess the main question then is there anything in principle that would block the extension from what I've been talking about is 0 plus 1 dimensions to 3 plus 1 dimensions quantum field theory? Like some things that occur in quantum field theory are continuous spectra and degenerate states. So we'd have to think about those things. But if there is no blockage, then this story opens the way for QQT to give a consistent continuum space-time description of super Planckian energies. QCD is already showing us what a UV complete theory looks like, UV complete quantum field theory. And so it seems like quantum gravity may look something similar. And the final question is did we give up on quantum field theory too early, like about 45 years ago? Okay, thank you.
So, are there any questions?
Do you have a path integral description?
Yeah, up until you try to extract the probability. So you can use the path integral to calculate all the correlation functions. And you get all these results of strange looking minus signs in front of propagators. But all those are completely defined by the theory before we even talk about the Born rule.
So what is the path integral?
It would just be the standard path integral with a minus sign in the kinetic term. And the I epsilon chosen so that it's always the Feynman choice of I epsilon.
Yeah. Thanks for the talk. As you know, in classical physics, there's something new that happens when you couple a wrong sign oscillator to a correct sign one. You get runaway solutions where both get more and more excited. Did you study analogous system in 0+1 quantum mechanics?
Well, first of all, that runaway solution, that runaway effect would be a property of the classical theory when you couple those two sectors, because one sector does have negative energies. But I'm talking about quantum theory where those two sectors would both have positive energy.
I understand, but I asked, did you study a system that had two oscillators coupled to each other?
Yeah. And in fact, I have. So I gave numerical results just for the pure ghost theory. And by using Kronecker products to define theories with more fields, I considered a theory with a normal field and a ghost field. And then I get similar results. Where
What interactions between them did you consider?
I considered interactions that were odd in the ghost, like these theories have phi cubed. So an interaction, something like phi ghost and say phi bar, which is normal, phi bar squared. Some interaction like that. Plus a phi cube ghost thing. So there you have two couplings. So then you have a bigger space of couplings to consider. And so in that case, I'm not claiming that any choices of those two couplings give a theory without complex energies. Complex energies may show up for some choices of couplings, but I found other ranges of couplings where it was the same as here, like up to 40 states, they were all real.
Okay, that's surprising. It's in one of the papers.
No, none of this is in any paper yet, but hopefully soon.
Okay, thank you.
Yeah.
Thank you. Any other questions? Yeah.
Well, I'm not sure whether I understand correctly. So are you trying to rebuild Born rule because because of ghost?
The ghosts give a negative norm and therefore funny probabilities. And so the Born rule, I said, was the only thing in the theory where those negative norms actually produced a problem. So then the idea is to change the definition of the Born rule, which means constructing a new inner product just for use in the Born rule to produce a sensible Born rule.
So the things work out just fine in 2+1D?
Oh, no, this is a question.
Yeah.
So I hope someone like you works on that question.
Any more questions? If not, let's thank all the people who raised questions and also thanks Professor Holdom again.